layout generation by multi-control net diffusion with decoupled geometric and performance control. So all the way from Hong Kong Hong Kong University of Science.
Yeah,
so
thanks.
Don't tell Chuck.
I will not. Okay, thanks for your introduction. My name is Wenli, and today I would like to share my work, the flat layout generation via multi-ControlNet diffusion with the decoupled geometric and performance control. Oh, sorry. Okay. My research domain is focused on the building energy consumption. We all know it's quite essential. And here we can see a fact that the buildings and related construction industry account for the 37% of the global energy consumptions. And for this, such a serious fact, we have proposed many sustainability assessment criteria to solve such challenges. And in this assessment criteria, we consider the energy consumption in the building designs, but in the traditional workflow to incorporate the building performance into the design process. Here we can see the main 3 steps. The first step is to generate some designs, and then we conduct the complex checking, and finally we evaluate their performance, and then goes back to revise our designs, and it's a very time-consuming workflow. And another way to solve that problem is to use some generative AI models like the diffusion model, but we need to consider 2 separate conditions. One is the geometric condition, another is the energy conditions in the same model in the model architecture. And in this figure here, we can see some current practice in the literature. And in this paper, they combined multiple conditions into the same channel and integrate the final integrated conditions as the input for the diffusion model. But this integrated method will combine all the conditions into the one channel to the model, and will not separate the different controls. But that's not incorporate for the geometric condition and energy condition, because sometimes the 2 conditions are conflict. And another way is that they are not independent, because the geometric condition maybe affect the energy conditions, energy performance. So how can we separate the 2 conditions in our generation and use the efficient diffusion model to replace the traditional workflow? Here is some advanced technologies. That is the ControlNet. In the ControlNet technology, we can see there are many ControlNet branches for the diffusion model. We can input different types of the constraints. And for example, the ControlNet for the semantic segmentation and the ControlNet for the depth map, and they can import the segmentation map and the depth map to the diffusion model, so that we can into the 2 channels, so we can separate the different aspect input, and combine with the current technology and try to solve the challenges. We put forward our research objective is to develop a sustainable performance condition diffusion model, and based on the multi-ControlNet architecture, so that we can consider the geometric condition and the performance condition better. And here is the whole workflow. And in this workflow, there are 3 main parts. And the first part is to prepare the data set and get all the energy labels of all the flat layouts in the data set. This is a widely used dataset, the R plan, and maybe many in the floor layout generation domains researchers use this dataset. But my work is enhance the dataset with the energy labels. And next step is to train the model to do the generation task. The main task here is to get the two inputs here, and so that we can import our requirements. And one input is the segmentation map to represent the geometric condition, and another input is here the energy depth map to import our energy requirements. And here is some detailed steps. In the first step, because we need to get the energy label first, so we need to convert the images in the R-plan dataset into the simulation model in the Grasshopper, like some simulation tools, so we can get their energy performance. And here we use the image-to-sim algorithm. This is from our previous work, so we can automatically convert all the flat layouts into the simulation models. And after we get all the energy labels, so here now we have the ground truth. One is the R-plan, the geometry layout, and another one is the energy labels. And so we have got all the ground truths, and next step is to prepare our input. When we're training the model, the input for the geometric condition, the semantic segmentation map is come from the ground truth. We get all the rooms inscribed circles to represent the room's location, room's type, room's number, the such information into these more images. Here we can see. And but when we after trained, the model is well trained. When we use the model in the real practice, the segmentation map we can draw friendly based on the logic of the architects. And the next step is the most important part in this work to prepare the energy depth map. This is because diffusion model is a visualization model, and the ControlNet also need to the visualization, the image format as the input. We also try to directly use the scalar number as the input, but the control of the energy performance is quite low. So in this work, we use this practice, convert the numerical number into a image to represent the energy performance. And here is the final output for this step, the energy depth map. And we use some detailed steps. For example, here we get the bounding box of all the room circles first, and square the bounding box, and use some Gaussian maps to generate mapping the energy performance with the energy depth map. So we can only use this figure to represent numbers control. And here is some visualization to show the relationships between the two inputs with the ground truth. We can see here each room will conditioned with this circle, and the whole energy depth map will control the whole layout. And here is the model architecture. Actually, in the whole workflow, I already showed this, and we will integrate the two inputs into the two separate control net, and then the diffusion can get the two inputs. And we, in the results part, we compare our model with some benchmarks like the pixel to pixel and the house diffusion. And we also compare with adaptive pixel to pixel, because we use the two inputs. So I revised the pixel to better a fair comparison. And from the results, we can see our model almost performs as the best model, even though there are some it's not best in this metrics, but it's quite close. So we can also say our model performs almost the best. And here is the visualization results compared with the benchmark and our models. Here we can see even with such irregular boundary, our model can perform well, but for other models, they are struggle with the walls between the rooms, or maybe some redundant parts. And here is this part results is to validate our energy control, how it controls the performance. And here we can see we use some metrics to say whether the results response to our input. Here in this figure is we can see directly when we increase the input, the energy performance in our input, our results can also increase the energy performance of the generative results. So this means our model can really control the energy performance of the generated layout. And here is the visualization. We can see the logic, how we model control the energy performance. Is try to revise the boundary whether it's loose or very compact. So that will change the shape factor, which is the most important metrics for the energy performance, so that we can control the performance. And the next part of the results is to validate the geometric controllability. And here we do 5 adjustments to validate this. And for example, here we change some room types or the room size. Room size is controlled by the circle's area, and we change these conditions and to see the response from the model, and we can see all the performance are good, and we can generate the corresponding layouts. And here are some other modification of the input, and all the modification can performs well in our model. And to summarize our work, we propose a decoupled multi-ControlNet diffusion model so that we can separate control the geometric condition and the energy condition. And we reach a high performance of the model training. And next step, we will also consider the 3D massing model, because we focus on the 2D flat layout and continue enhance our energy label data set. And that's all for my today's presentation. Thank you.
Okay, thank you very much. Any question I have?